So, buongiorno, everybody, and welcome to iChem. Today, we want to get into something called kinetics. So, let us start here with this consider. So, speaking of Italy, let's think about Romeo and Juliet. Consider Romeo and Juliet. And we have our love-struck Romeo, and he wants to give Juliet a passionate kiss. Not a passion kiss, a passionate kiss. What must happen for this event to occur? Okay, so let's think about this. Here's Romeo. He's singing the streets serenade, right? And he's fallen in love with Juliet and he wants to lay a big smack right on her, right? So what's the first thing that Romeo has to do? Well, Romeo must first do what? He has to run into Juliet, right? If he just has his lips out and he's walking on this way and runs into a tree, well, that's not going to be a very effective kiss for Romeo. So the first thing that must happen is that Romeo and Juliet must crash into each other in some way. Well, maybe not crash, but they must have contact, right? So we must have contact. Now, number two, what else must happen? He wants to give Juliet a passionate kiss. So is it okay if Romeo runs into Juliet's elbow? No, that's not going to be very effective. What if he runs into Juliet's shoe? No, that's not going to be very effective. What if he runs into the top of her head? She's not going to be very happy with him smooching her right there on the top of the head. So not only do we need contact to have an effective kiss, we've got to have proper orientation. Okay, so we have to have two things to have a good passionate kiss here, and that is we first have to have contact. Second, we have to have a proper orientation. So that means I need to have Romeo with his lips. Yeah, it looks like a chicken, Romeo. Eeks. Okay, here's a nose, and there's the lips, and then we have to have Juliet. Here's her nose, and here's her lips. Juliet's not much of a good looker, is she? Okay, well, Romeo's not much either. Good. So here they are. So we have Romeo and Juliet, and we have we have contact, and we have the proper orientation. But for this to be a passionate kiss, what else must we have? Well, it can't be just a little peck. It can't take like a millisecond for this to happen. This has to have enough energy, right? This has to have a minimum amount of energy for this to be a passionate kiss. So the third thing we need is sufficient energy. Great. So for Romeo to plant a great passionate kiss on Juliet, we've got to have contact, we've got to have proper orientation, and we have to have sufficient energy. Good. All right, so now let's move on. Let us consider this reaction. Solid carbon reacting with oxygen gas to produce carbon dioxide, right? Okay, so let's illustrate this reaction. So here I have a big blob of carbon. That's my carbon molecule. And here I have my oxygen, right? And we have an overlap here. And we probably, okay, we'll just leave it at that because oxygen really is kind of a funky arrangement. And what do I get on this side? Carbon dioxide. I have a carbon and then an oxygen and an oxygen overlapping that carbon, right? So what must happen for this reaction to occur on a molecular scale? First of all, I've got to have contact, right? Number one, I've got to have a collision. So my carbon has to fly into my oxygen. Now, can it fly into anywhere? If my carbon comes around and hits right here, is it likely that it's going to end up in the middle like that? No, probably not. What if my carbon comes around and hits right there? Is it likely that I'll end up with this kind of arrangement? No, probably not. Now, neither of these two seems very likely. In fact, I am oversimplifying this, of course. But what if my carbon came right there and smacked right there? Well, then it could force my two oxygens apart, and my carbon could slide in right between, and then they can overlap, right? And then I would have my oxygen, carbon, and I would create that molecule. So first thing I have to do is I have to have a collision. Not only that, I have to have a proper orientation, right? And the third thing is, what if this goes very weakly? Boink, 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 it hits that. Well, it could just bounce off. Or if it hits there just very weakly and bounce off. The third thing I must have is that this collision must be forceful enough for the reaction to occur, meaning I must have sufficient energy in collision. So, to summarize, I have to have collisions with proper orientation, and then I have to have collisions with sufficient energy. So those are the three things that I must have for a reaction to occur. So these are for a reaction to occur. What must I have? Collisions with proper orientation, and collisions with sufficient energy. Cool. Now, what are we talking about here? We're talking about collisions, we're talking about reactions, we're talking about Romeo and Juliet. Really, here we are talking about kinetics. And so let's talk a little bit about kinetics. What are kinetics? Kinetics is the study of reaction rates and reaction mechanisms. Good. And let's just dissect that a little further. What is a reaction rate? Okay. What is a reaction rate? So here is my kinetics, and then I have reaction rates. What are reaction rates? Well, this is the change in concentration per time. Okay, change in concentration per time. Now, what concentration? This could be change in concentration of a reactant per time. Yes, change. How do I say change? Deltas, there we go, delta. Change in a reactant over time, or it could be change, that delta means change in the concentration of a product over change in time. Okay, or you could write it kind of like D concentration over DT, and D concentration, this is reactants, this is products, over DT, and that starts to look like what? Ooh, no, don't tell me. Yes, calculus. Ah, good, but we're not going to go too much into calculus. So that's reaction rate, change in concentration per time. And what is a reaction mechanism? Reaction mechanism, because this is also studied in kinetics. A reaction mechanism is really a step-by-step explanation of how a reaction occurs. And to give you an idea that the reaction we showed earlier, we said, hey, carbon reacts with oxygen to produce CO2. Well, I could say that this happens in a different way. I could say that two carbons react with O2 to form two COs, and that could be step one. And then what's step two? Step two would be two COs react with O2 to form two CO2s. And that's step two. And then when I add these all up, what do I get? I get two carbons plus two oxygens yield two CO2s, because these guys cancel. And so this is a mechanism to explain step by step how that reaction could occur. And then the first step, this happens, second step, that happens. Hey, and by the way, this thing here that's created and then later destroyed, we would call that an intermediate. Now, we don't care about that for honors, but when we get to AP, that'll make a difference. Good. So that's kind of kinetics. And then we actually learned something else already today. Let's go down here. And that is what? Let's talk about prerequisites for a reaction. What must happen for a reaction to occur? Number one, there must be collisions. Must be collisions between reactants. Number two, these collisions must have must have a proper orientation, whatever that is, a proper orientation for the reaction. And third, it must have, the collisions must have, sufficient energy for the reaction. Okay, great. Wow, we learned a lot already, and all this is because of Romeo and Juliet. Woo. All right, let's go farther then. Did we cover this thing here? No, 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 no. That one's all done. What's next? Blank. Oh, here we go. So consider a lump of carbon reacting with oxygen at 190 degrees, 195 to form carbon dioxide. Okay, so we know the reaction. I have a lump of carbon plus oxygen gas, and it's going to form carbon dioxide gas. Okay, and it's a lump of carbon, right? So that means I have a big blob of carbon. Here's my big blob of carbon, right? Carbon. There's a bunch of, really, there's a whole bunch of carbon atoms in here, and it's all a big, like a piece of charcoal. You know, that's what we mean by a big lump. What happens to the rate if the lump of carbon is crushed? So I'm going to crush this, and so that means my carbons are now kind of lined up more like this, right? That they're all lined up like that. So what happens now to my rate? Okay, now let's go back and think of what's necessary for a reaction to occur. I need to have collisions. I need to have collisions with a proper orientation, and I need to have collisions with sufficient energy. Okay, so let's talk now about, let's go this way. I'm going to use green to cut through right in the middle. Yeah, we'll cut through this way. Ooh, serpentine. Good, and we come right here and effects on reaction rate. Okay, so what things can affect my reaction rate? Well, we have to have collisions. So if I have more collisions, I'm going to have a faster reaction, a higher rate. So we want to increase collisions. And one way that I can increase collisions is that I can increase surface area. And this usually has to do with solids. Increasing surface area, that means I want to have more of the surface, more of my molecules exposed to the other reactants. And as an idea is something like a block that has low surface area, whereas powder, if I pulverize something, that has high surface area. So the flatter, the more individualistic I make my particles, the easier it is to react. So as my surface area increases, what happens? My reaction rate increases. Now, why is this? Think about that. Let's say that I have one molecule. Let's say this dark guy. He's in the middle, three-dimensionally, okay? He's in the middle of this box, so that's a nice three-dimensional box. Good, I should have brought it down here, right? There we go. But he's floating around in the middle. Well, and here he is right here. Okay, so now I have red guys that are trying to react with him. Well, this red guy, how does that red guy ever get to him? Well, these red guys have to start reacting with all of the green guys on the outside, and then the next row of green guys, and then the next row of green guys, and it takes a long time until all the green guys are out of the way, so finally one of the red guys can go in there and react with him. Well, in this case, a red guy can come right down and bam, pop, there he is, and he's already reacted. So when you have an arrangement like this, more of your reactants are open, available, more reactants available for collisions. Got it? So as my surface area increases, then I have more area, more reactants available for collisions. If I have more collisions, what happens to my rate? My rate increases. Okay, so let's explain that. Surface area goes up. What happens? More molecules available for collisions, and if I have more more molecules available for collisions, collisions. I don't think it's spelled collisions right. Collisions. How's that? If I have more molecules available for collisions, then I'm going to get what? More collisions. And if I get more collisions, that means what? Rate increases. There we go. So what happens when my carbon is crushed? My rate increases. Got it? What happens to the rate? Let's look down here. What happens to the rate if the concentration of the oxygen is increased? Okay, so let's talk about concentration increase. This is effects of rate number one, surface area. Number two, let's talk about concentration of a reactant. Well, if my concentration of my reactant increases, what does that mean? Well, that means there are more molecules of reactant per volume, right? So that means they're more concentrated, right? There are more molecules per volume. Now, what does that mean? I have one or two. Let's say I have this block right here, and I have 3 blacks, and I have 1 red, and we need to get collisions, right? Versus, let's say I have the same size block, but I have this many blacks and 1 red. In which of these cases, and this red is going in all directions, right? He's just like a gas. In which of these is he more likely going to hit a black? In this one or this one? Well, clearly, the probability is he's going to hit a black much more frequently here. So if I have more molecules of reactant per volume, then I'm going to have what? More collisions. And if I have more collisions, what does that mean? That means my rate increases. There we go. So you increase a reactant concentration, you get more collisions. More collisions means rate increases. Good. So here we go. What's the I increase the concentration of my oxygen, which was a reactant. I have greater concentration of that. What's going to happen? My rate increases. All right. And what happens to the rate of reaction if the temperature is reduced? So I'm going to reduce my temp. All right. That's going to be a third effect, temp, right? Zoink. Temperature. What effect will temperature have? Well, let's say we've increased everything, so what's increased temp? What happens if I increase temp? Well, we know that temp is related to what? Average kinetic energy. So my average kinetic energy increases, and average kinetic energy is related to what? The velocity squared. So the velocity of my particles is increasing. And if my velocity is increasing, what does that mean? Well, number one, if my velocity is increasing and this guy's moving faster, what's going to happen? There are going to be more collisions. And what else? Let's go back up to here. What else is important? Collisions. Okay, we talked about that. Orientation, sufficient energy. Aha, if I have a higher velocity, that means there's going to be more collisions with greater impact, right? And so that means more collisions and more collisions with greater impact, which means what? With sufficient energy. So I'm going to have more collisions with sufficient energy, and if I have more collisions and more collisions with we will put that and. So we have more collisions and more collisions with sufficient energy. What does that mean for my rate? My rate will increase. Cool. All right. So in this case, what happens? I reduce my temperature, so that means my average kinetic energy does what? It decreases. That means that my velocity of particles decreases, which means I have fewer collisions and fewer with sufficient energy, which means what for my rate? My rate decreases. Cool. Okay, is there anything else here? What happens to the rate if a suitable catalyst? Okay, let's talk about catalysts. Catalysts are easy. The fourth thing that can affect our rate, catalyst. Okay, first of all, what is a catalyst? It is something which increases rate of reaction, but which is not consumed in the reaction. Let me put permanently, and we may learn something about that later. So it is something which increases the rate of reaction, but which is not consumed permanently in the reaction. Okay, so that's what a catalyst is. Cool. Now, what's its effect? Very simple. I kind of said it already. Addition of a catalyst, when I add a catalyst, usually what happens is something called the activation energy is lowered, and we'll get into that later. And because the activation energy is lowered, the rate increases. But just EA for activation energy, the EA is lowered because of the catalyst. Got it? So what's the effect? Catalyst lowers the activation energy, and by doing so, the rate is increased. And we'll talk about activation energy at the end of this unit. All right, so here we go. What's my answer? My rate increases. Woo! All right, here you go. You guys give this one a shot and bring me back when you're ready. What three things must happen? Easy. Got to have collisions between H2 and O2. I've got to have a proper orientation in these collisions. And what else? I must have sufficient energy in these collisions. Good. There you go. Those are the three things. Now, list 3 ways to increase the rate of reaction. Okay, what's one thing? Well, I could increase the concentration of H2. Another thing is, what could I do? Increase the concentration of O2. What's the third thing I can do? I could, 3, increase temp. 4, I could do what? Add a catalyst. And really, there's not much way that I could mix these perhaps better, and that would give me an increased surface area, but not really. There's really, yeah, that's not even a right thought, sorry. There's really nothing much I can do to increase surface area of gases, okay? So surface area doesn't apply to this one. All right, well, that's kind of the basics of kinetics. Let us stop here, and next time we'll start talking about exothermic and endothermic. Have a good day, y'all.